And I love these guys. I got to tell you how much I love these guys, because they get it. Do you think these engineers need that video to understand what's going on? Truth is, they don't. That's for us, right? They're doing that for us. They get it. They understand what it is we need to see. They understand how to package it and couple it with the engineer stuff, right? So we can build it. We can take it. We can use it. And it gets even better. Steve's going to make it even better.
Thanks, Pete. I have the great privilege to back cleanup for these gentlemen, and they battled through a lot of it, and we're going to bring it down to the realistic, take it out into the field, and take it to the street-level firefighter, give them a chance to see what's going on. And that's what really drove this next set, was you can sit out here, you can see the experiments we did in the lab, and yeah, it piques your interest, gets you thinking about it, but again, like Dan said, you don't fight fires in the laboratory. And that's what took us to Governor's Island. We, not to be outdone, the fire department in New York, after we got buildings with Toledo and Chicago, they got us an island. And we got a 7-story building on this island to essentially turn into a laboratory. And what we want to do in our laboratory is we want to expand on what we had seen previously. We wanted to take the PPV experiments that we had done in Toledo and Chicago and expand them to make another data point. How do they work in a 7-story building? We did it in a 30-story building. We did it in a 16-story building. Let's try it in a 7-story building. Let's look at pressurizing stairwells. Let's look at maintaining conditions in the stairwell for the occupants to egress and the fire department to set up their operations in a more tenable atmosphere. What can we do in this building, and how do those fans work against wind-driven conditions? What tactically needs to be done in order to use that successfully, and can things happen where that's not the tactic to use? We looked at wind control devices again, both the blankets and the curtains, to get an idea of how this works vertically. We start lighting fires on the 7th, 5th, and 3rd floor. What kind of conditions do we see? And then alternative strategies of attack. So the floor below nozzles, introducing water, flanking it from a safe location, looking at different streams, fog streams, smoothbore streams. How do these different things impact conditions in the corridor where the fire department would be advancing sort of as a plan A? Let's start validating these tactics for plan B. Plan B should not be to send engine company after engine company down that hallway, burning them up until the fire goes away and they can walk in and put it out. We need a plan B. Here's our island. You can see our 7-story, as Jerry will say, your fireproof multiple dwelling. And we turned this into our laboratory. Right there in New York Harbor, right off the tip of Manhattan. To give you some orientation, the closest point on land to the face of the Statue of Liberty. And got the opportunity to turn that into a laboratory. Here's the floor plan. 2 identical sides of the building. We wound up being 14 experiments in 12 different apartments on the 7th floor, the 5th floor, and the 3rd floor, starting at the top and working down, looking at these different tactics. We ran miles and miles of cable to measure temperature in the fire apartments, temperature in the corridors, gas velocities, how quick are these air currents moving through this building. If you open different doors, if you open your bulkhead door, you open the base of the stair, what does that do to the flows in the structure? When might you want to open the bulkhead? When might you not? Try and answer all these questions. We got all of the upper echelon of the New York City and Chicago fire departments to start putting together what-if scenarios. If you were to implement these tactics, what would you want to know ahead of time as opposed to trying it for the first time on the fire scene? It's not the time you want to be experimenting with things. So we implemented all of their questions, all of their suggestions into these 14 experiments to start answering some of these questions. And we're going to go through some of them tonight. The bottom line is you've got a 600-page document and hundreds of hours of video to answer those questions. And that's something that we're going to pile through. Here's a couple of shots real quick to give you an overview of what we did. We wanted to simulate the wind, and one of the reasons this building in particular was interesting was that probably 360 days out of the year it's subjected to wind, so we'd have an opportunity to run some experiments with some natural wind. as opposed to having to make the wind like we did in the laboratory. Well, more than half of the days we were there was no wind. So we had to improvise, and we used the mobile ventilation unit that you see in the two pictures on the side there. That gave us an opportunity to make a known velocity going through that window. We knew what the wind was, and we were measuring it continuously. And we actually got a few natural wind conditions as well, when we'll look at a couple videos of them. You can see the furnishings of the apartments. We use similar furnishings that we used in the laboratory, so we can start connecting the points here, understanding what the energy release is in the structure, and moving from that. So you can see a furnished living room and a furnished bedroom there. All of these apartments were furnished throughout and were done repeatedly 14 times. Here's a quick video showing an outside view where our fire was in the bedroom right here. And we're looking from the bedroom, our simulated wind blowing in through the bedroom, down into the living room. So you can see the flames starting to blow through the living room, starting to involve the living room. The public hallway, where you've got flames just rolling down the corridor, and then you've got the stairwell door open and the bulkhead door open as well. And you've got flames all the way from the bedroom, more than 150 feet away, coming into the stairwell, with absolutely no fuel, with the exception of paint and concrete in between the living room and the stairwell door. And you'll see here, the living room window fails. Very important on a size up to see all sides of the building. Just because you have no flames, or you've got flames pulsing out of the B side, and you've got flames venting extremely quickly out of the A side, doesn't mean that you've got a naturally ventilated fire and there's no wind conditions and everything's okay. It's important to see all sides of the building. And the other important thing was, even when that living room window failed, sort of creating the path of least resistance, sort of a 6-foot by 8-foot opening in the side of the building, there was still enough flow to completely split going out that window and still producing flames through the hallway into the stairwell. So you're talking a serious amount of air moving through this building that you don't want to be in the way of. First thing we looked at, positive pressure fans. We know we have the ability to use them successfully to protect stairwells in a non-wind-driven condition. How do they work in a wind-driven condition? And we looked at a number of scenarios. The fans we used here, 27-inch portable fans, similar fans that we used in all of our other experiments, sort of the largest portable fan that you can wheel around and use somewhat easily. And the important thing there is to purchase fans for your application. If you're going to pressurize high-rise stairwells, you don't want to do it with a 16-inch electric fan. It's just not the right tool for the job. And if you watch that DVD, you'll understand that stuff a lot more. Here's an 8-view video looking at one of the experiments. And this fire started in the living room. The living room was well involved. And right now, we're pressurizing that stairwell with a single fan at the base of the stairwell. And you'll see we're going to turn that fan off, and we go from a completely protected stair to, within seconds, that smoke's coming back down the stairwell, creating conditions that are not suitable or that you wouldn't prefer, just sort of showing the ability to pressurize a stairwell. When it comes to wind-driven conditions, the fans were effective at holding the flow around the door, sort of like what you saw in the IR view in the stairwell. But as soon as you open that door, that's too much flow coming in against that fan. But the fan slowed it down and created better conditions with lower temperatures in the stairwell. Very important to utilize that tool. Here's a graph looking at temperature. So you've got your temperature in Fahrenheit on the right-hand side here. And this is an idea of the scale of one of these experiments, and sort of in the lab, we could really control fire grows, open a vent, what was the impact of that vent, or drop a curtain, what was the impact of the curtain. Here we've got 7 floors to work with, and we wanted to replicate what the firefighters would do as they arrive. So everything from opening the base of the stair to access the attack stair, opening the fire floor, opening the bulkhead, turning fans on, turning fans off, all of these things we wanted to get a look at. But here we're highlighting the use of the fans. So here you can see as the fan's activated, what it does to the temperatures, mainly in the stairwell is what we're looking at on the bottom here. And it drops temperatures up in the 200 degrees Fahrenheit back down to ambient very quickly. And what you saw on the video was what happens when you turn the fan off that was protecting a stairwell that had ambient conditions. You turn the fan off and you're allowing that flow back into the stairwell, and you're in the 300 to 400 Fahrenheit within seconds of turning that fan off. So utilizing the fans to protect your stairwells is an absolutely significant tool when implemented properly. Wind control devices. Here's a closer look at the two wind control devices that we utilized. You've got what we'll call a blanket implemented here over the double window. Usually requires 2 firefighters on the roof and a firefighter or 2 on the floor below to hold the straps on the corner and essentially drop that blanket over the window, shutting off the wind. And that stows sort of getting folded up in a small package. And then you've got the wind control curtain here, which has ribs in it, some metal rods in it, which allow it to stiff across the window opening. And this can be deployed from a single firefighter from above and anchored from a single firefighter below with the corner straps. And that rolls up. This is 6 feet by 8 feet. This is 10 feet by 12 feet. So you can see the scale of the two wind control devices there. I'll show you a video here of a wind control curtain being deployed. We've got a wind-driven condition going through this bedroom out into the public hallway. It's going to vent the living room window. So you can see the flames coming a significant way out the window. You cut that air off, you cut that oxygen supply off, and as they get it in place, that's deploying it. It's almost like somebody's putting water on the fire. You cut the air off, you kill the fire, pretty much knocks whatever fire was in that living room down. You remove the wind-driven condition and pretty much go back to the room and contents fire that you started with before the air was introduced. And that's a pretty good example right there of how that device is deployed. And in this case, it was deployed off the roof. It could easily be deployed out of the 6th floor over the 5th floor, or out of the 40th floor onto the 39th floor as a tool to cut the wind off. Here's what that looks like in Engineer Ease. So you've got our temperatures here, and we're in excess of 1,500 degrees in the bedroom. So in the top, we're looking at the bedroom. As we get down here, we're looking at the corridor temperatures where the fire department would be making their way down the hallway. Here, we're looking at stairwell temperatures. And pretty much before that wind control device is dropped, you're in excess of 1,500 degrees in the bedroom. You're in excess of over 1,000 degrees in the corridor, completely untenable. And you're up above 600 degrees in the stairwell, also untenable for firefighters. You drop that wind control device, cutting the air supply off. Essentially, you cut the temperature in half, if not more. And removing that wind-driven condition, again, allows you the ability to go ahead and implement your direct attack down the corridor. Floor below nozzles. Here's something that we couldn't really extensively get a look at in the laboratory because we really didn't have a floor below. We looked at sort of laying in front of the window and shooting the water in. Here we had the ability to essentially take tools that were in the minds of firefighters and welded together in their spare time and made on their own, and get an idea of what these things could do, how we can implement these floor below nozzles and what impact they can have. And you can see two different kinds here. You've got the one that comes up from the floor below out the window and hooks on to the window sill on the floor above. And then you have the second kind that essentially has a 60-degree bend in it, sticks straight out the window on the floor below, bends, and as you adjust it out the window to the correct distance, you get that angle, and the water will direct itself right into the floor above. sort of the plan B. We can't make the fire floor. What happens if we introduce water to the seat of the fire? And that's what our experiments looked at. And we also looked at the impact of a narrow fog, a smooth bore, other fog nozzles, different sprinkler type devices to see what would work best, what would have the most impact. Here's a quick video showing another wind-driven fire. What's important is what's going on in the public hallway. What's going on where the firefighters are trying to attack this fire from. You see the floor below nozzle stuck out the window here. And once we get to the right point, they're going to charge that line. They're going to adjust the nozzle so they no longer have water coming back down. All the water is going into the floor above. No firefighter has to hang out the window on whatever floor. And you see the second that water goes in that window, wind-driven condition goes away. You knock out those gases like we saw in the laboratory. Get some water on the seat of the fire, your problem starts to go away. And this is the ability to put water on the seat of the fire remotely. And one of the beauties of this nozzle right here is that that can quickly be deployed from the floor below, just like you would stretch a standpipe line, and you can direct that water into the bedroom. And if the fire's going in the living room or conditions aren't getting better, you can easily move that right out to the side window, go out, put water in the living room, very quick, get a knock on it, get your crews up to mop up. Here's what that looks like in data. Again, temperatures in the corridor, which is what's really important, in the excess of 1,200 degrees. Flashover conditions in your public hallways. You can't advance on that. Stairwell temperatures up in the 1,000-degree range, something that you can't advance on. The second that floor below nozzle hits the seat of the fire, drops the temperatures pretty much from as high as 1,000 degrees down less than 300 degrees Celsius in seconds. Validates the tactic very well, and this was done a number of times. I'm just showing you one example. We talked about the natural wind. One of our concerns was that we were over-simulating the wind. Here's a natural wind blowing into a bedroom fire. And to talk about pulsing, here's a prime example right here. If you pull up and you're the incident commander or you're the first arriving engine company and you're assessing the conditions you have inside and you see pulsing fireballs coming out of the window and going to the ground, you need to consider your wind condition. This is a great example of something you might see on a size up. And as it turns out, what we were doing in this experiment was taking the natural wind, allowing it to go through an apartment on this wing, through the corridor, and out of an apartment on the other wing. And it got to a point where conditions deteriorated so quickly, we essentially had to evacuate all the crews that could deploy the blankets from the floor above because almost the entire floor was about to flash over simultaneously from one end 400 feet away at the other end of the floor. And conditions were extremely bad, and this is what they look like out that window. And it turned out that the simulated wind was right on par, if not underestimating the ability of the natural wind. So this sums it all up. Wind is part of size up. This is an important one. If you don't realize there's a wind condition on your arrival or make that as part of the continuous size up of the crews as they're operating, sometimes you might have no wind on the first floor and have a significant wind on the 30th floor. That's not uncommon. That's something we've seen fairly frequently. The ability of the people operating on those upper floors to give that return that they've got a wind condition on the floor above the fire, to make everyone aware, to start checking their doors, paying attention to the flows that are coming underneath the doors, to understand the ability of that window to fail and conditions deteriorating quicker than you can react. Extremely important. Controlling doors in the flow path. Every door that you open and leave open is contributing to fire behavior in that building continuously. You open the base of the stair and chock that door open, you just change the airflow dynamics in that building. You open the bulkhead door, you leave that open, you change the way that fire is going to grow and react. One of the biggest conclusions that's going to come out of this is the impact of vertical ventilation in these stair shafts with fires that may be 5 floors remote and on the opposite side of the building of where that stair shaft is opened. You want to get a fire to grow and to flash over, open the bulkhead door, open the stairwell, and allow it to vent vertically. That will allow that fire to progress much quicker than if you left that door shut. Positive pressure fans. Improve stairwell conditions in every single orientation. Fireproof building, we're not talking positive pressure attack, we're talking about pressurizing a space to control where smoke can flow to or slow down where that smoke is going to go to. It's always a good idea, or the common thought process is we're going to have an attack stairwell, we're going to have a ventilation stairwell, and no occupants are going to enter these stairwells, or we'll be able to keep all the doors shut and no smoke will get into the stairwell. We'll get all the occupants down, no problem. If anybody really gets that to work effectively and can keep the smoke from leaking around the doors into the stair shafts, that might be a viable option. Most of the time that doesn't happen. Using technologies such as pressurizing stairwells, which get used daily when buildings are engineered, can really help you out. Wind control devices, stop the wind effects, improves thermal conditions, doesn't put the fire out. That still needs to be done. Floor below nozzles, put water on the seat of the fire, improve thermal conditions, doesn't make the oxygen supply go away. Combining tactics works great if you can combine the blanket deployment with the nozzle, get all these things working together, but it's extremely labor intensive. And each of these tactics requires staffing to implement. That's something that needs to be examined at the fire department level. Take it to the street. These guys are going to talk about that. How many people does it take to deploy these tactics? What staffing do we have available? Could that staffing be used for other things? It's all important things to take into consideration as you do your size up and look at your resources for these hazards. I'm going to turn it back over to the chiefs, and we're going to wrap it up.
I love this stuff. I mean, can you imagine telling a bunch of firefighters, I got this great new firefighting technique, we're going to block all the ventilation openings. They look at you like you got 2 heads, right? What, right, you see, right? And then another one, I got this great firefighting technique. We're going to throw water on the fire from outside the building, right? What do they tell you? You're going to push the fire. Guess what? It's being pushed pretty effectively by the wind, right? Instantaneous reduction, going from an unwinnable, unfightable, unmanageable situation to something we can deal with 2 really simple techniques. Aren't going to put the fire out for us, but they're going to make it fightable now, right? Go from not fightable to fightable.